Good afternoon. We're going to start our next session now. System level design approach to meeting intrinsic safety in single pair Ethernet. Our speaker is Pran Haran, CTO of Smart Embedded Systems. Pran has more than 30 years of experience in leading engineering teams in successful development of products from conception to production. He has led embedded software and applications development for many successful companies, such as Euphoria Networks, Force Computers, and Smart Modular Technologies. He brings great experience in managing multi-site product development and agile methods.
Thank you. Simply Ethernet design, working on intrinsic savety zone with people, there are strict power, maximum power requirements. There are restrictions on how much inrush current it can have and so on. So in our design, to manage these competing objectives, and I will go over what are the design issues and compromises we made in order to meet the different requirements. So what is Ethernet API? So Ethernet is a single pair Ethernet device, mainly to be used in field devices. It provides Ethernet-based communication. It provides two-wire communications to the sensors. Power is supplied on the same two wires as what's carrying the signals. And wherever possible, the goal is to reuse the existing cable installations in already existing factories and processing industries. So additional functions and requirements of Ethernet API. Yeah. One of the important need for APL is to be able to operate in explosive atmosphere industries. There is gas, between the gases or gas and other pollution, which can provide safety related issues. And we also need to be able to replace failing devices without having to shut down the process. And at the same time, because of the ability to communicate faster, we need communication speeds between 10 milliseconds to 2000 milliseconds, depending on the process and the task. The other requirement is not only we are going to be supporting field devices, we need to support multiple protocols on different field devices. So, for example, Graphene, Ethernet IP, all have to be supported using this single wire pair Ethernet protocol. And all protocols have to be interoperable on the same physical network wherever possible. So let's compare the difference between standard Ethernet and in Ethernet APL. As you can see, typically Ethernet of the 100 megabits, it uses two, sometimes or four wires. And in the case of APL, the maximum rate is 10 megabits per second. It runs on two wires, and the power is supplied on the same wires as the two wires carrying signals. And there are devices and three switches, just like in the standard Ethernet. So, what are the considerations one must have when you are deploying Ethernet APIs? The first is what kind of PH devices that are going to be used in this Ethernet API. For example, the temperature sensors, pressure sensors, level, flow, other measurable values such as pH and so on. All kinds of sensors are possible. And if you're doing a control system, flow control and positioners, valves, all that are possible as well. And if typically API network, you also have switches, controllers, the data monitoring edge gateways, all will also be there. And typically the field switches, if it connected using shunt lines, and field devices will be connected to sport lines. And KT controls can be connected upstream. And the other, when you are designing an APL network, you have to consider the structure of the APL networks. I think Sean inside the earlier presentation covered the different aspects of the structure, the channels, the switches, and so on. So the structure of the APL network is important in integration, and the location of the field devices. Are they going to be in just in safe area or non-intrinsic area? That has to be part of the consideration. And then the connector types. We heard Sean mention M8, M12, and other type of connectors. Some are suitable for intrinsic safe area, some are not. So we have to keep that in consideration as well. And of course, safe area not is part of the consideration also. And then the control systems which manage all this have to be part of the network as well. So the applications, what kind of applications? And so we're talking about flow control, temperature controls, and then in capabilities of course, transfer. These are the terms commonly used as devices used on the typical APL network. And types of connectors, the operating areas such as zone 1, zone J, and even within the zone, what kind of class of devices are. And then the API is agnostic of the protocol. Whether you're only confident, you can type V hard, it will be CPA or any other protocol that's going to be running in server. So now on the ABL classes, I'm going to focus primarily on the devices at this time, because that's primarily what we develop and support our customers with. So I will focus on just the device power classes. I think Sean Vincent from HTG covered different power classes on the switches and so on. And I'll cover primarily the devices here, where there is the devices are typically what are load type of devices. So there is A, when they still primarily operated in intrinsic safe areas. Then there is C, and then there is 3, which is used on one intrinsic safe area. And primarily our company Smart Internet System makes a gearing module for power class A. So what is so special about the power class A? The power class A is the device with the lowest power, as well as to the most safe area where the devices have the ability to operate. And the maximum power available is 540 milliwatts. And typically, it's not a lot of power for many of the devices. So the design considerations are very critical in ensuring that the design that you're proposing very be within the power budget allowed by the system. So the first thing is we get an input power at 9 to 15 volt range, and then you have to convert that for all your devices that are operating in your center nodes. So typically it could be a microprocessor, some memory, some programming gain amplifiers, other converters or analog to digital converters, maybe some relays, LEDs, all that have to be managed within this power budget of 500 milliwatts. So first thing is there to convert the input power from 15 volts down through our operating voltage, maybe 3 volts, maybe 1.8 volts, whatever it is, the conversion has to happen. And typically in any of the voltage converters, you are going to lose about 20% of the power is going to be lost to conversion effectiveness. So the available power to your system, total power availability system, is only about 432 millivolts. And your Ethernet 5G, which takes 1 volt peak to peak signal it has to drive, it needs about 60 millivolts. And then your microprocessor, which is going to be running typically like STM32, is more, and then you've got some IO circuits for controlling or reading and so on. That needs some power. And in our system, you're operating in 60 megahertz, and that draws about 230 or so units. And if you're going to have SPI or other interfaces for controlling memory or other devices, you're going to need 30 milliwatts for the SPI interface. And typically, we're left with about 100 milliwatts for your sensors. And for people who work in 4 to 20 milliampere, they know that's not an unreasonable moment of power because typically 4 milliampere heart will work around 40 to 60 milliwatts. It's extremely low power. So we didn't have 120 milliwatts. It should be pretty good for most sensors and maybe even some small devices now. Before I go to that, so we also have to make sure the design operates and steer to whatever the maximum operating temperature is. So typically, as the power consumption goes up at higher temperatures, so you have to make sure. So whatever your design is at 25 degrees C, you have to make sure that you have sufficient margin at 70 degrees C. So you must have some headroom in your design to make sure that your operating temperature range is taken care. So whatever sensor we are designing, please allow enough room for room sensors. So now there are other requirements for intrinsic safety as well as the electrical compliance for APM physical layer. And one other is the rush energy when you apply the power. So typically you can put a large capacitor if you want to store energy for any fluctuation, but you cannot put too large a capacitor because it limits on how much energy can be stored because in exposure atmosphere, the total energy that's available for any kind of ability to generate spark or other things has to be kept below a certain threshold. So that amount of energy is about 500 microjoules. So any capacity you have that's hanging on the input power has to be within that only. And we also have to support any kind of voltage spikes and others. So the input signals have to be protected and that be careful of protecting against 25 milliampere, 25 ampere rush time and pulse shape of 20 microseconds for IEC standards of the SASP. As well as there are current changes. Anytime you typically switch on a relay or switch on an MED or even accessing some high speed memory and whatever the case may be, you are going to have some current fluctuations. So you want to make sure in the design, the current spikes are minimized as well. And you can use some amount of capacitor on your secondary voltages, but we also have to make sure that your input current spikes are minimized as well. So the point I'm trying to make here is there are electrical constraints that have to be kept in mind when you do the design. So that's aspects of the electrical design. So now coming back with other issues on the system design. So you are running a microprocessor only at 16 megahertz. And as you can imagine, it's not like a lot of computing power, and but you still have to get a lot of stuff done. So typically in a system like this, you are running a network stack, we are going to be running encryption, we are going to be running your sensors, maybe some algorithm running on your analog sensors for trigger to do some processing so that you maximize your signal to noise ratios and so on. So you have to make sure that you need some low overhead RTOS that can handle them. On the networking side, you are going to get multiple connections. For example, in HART, you have to support 5 simultaneous connections are very help. So we have to make sure that the implementation allows for all of them. And then the minimum update time in HART is 32 milliseconds, and that's about 53 updates per second. If you don't mean 32 millisecond response time, you're in very hard compliance for users. And which means if you got five clients, each of them needing this update time, we can roll out support in Calculator. And then, of course, we have to support some encryption for necessary other encryption methods. And so typically you have to use hardware acceleration for supporting the encryption. So the network stack has to be very lightweight, low work, and complements deploying memory preparation. And of course, if that is automatically means you have to minimize copies and others so that you maximize your performance. And for example, even LED may be a luxury in some other designs. So you probably have to make sure even the LED you are lighting up or indicating something won't draw more than 5 to 10 milliwatts because that is important for boosting the power. So this is one of our designs. For we use a streaming 32 microprocessor. We use 31 L chip from the technical instruments. And our total power consumption of this design is only 330 milliwatts. I think it's sufficient wood for adding additional sensors and some overhead for temperature as well. We provide able to provide an update of then 1 per second. Typically, we can get 50 to 60 against updates per second on this system. And we also have serial support for hard or Modbus or evening. On the APL side, we can support Profinet or hard. And then the design has got support for private and studio and other digital I/O optimization. Since it's a standard STM32 processor, customization and other features are all possible. We can give some contact information and 3 months. Then give you some more and answer any questions approved. One thing is what we use on this design, we use the embedded module. So if the customer needs just a module by itself, want to build a board, carry a board, the implementation is possible. Any questions?
Does anyone have any questions?
Correct.
Hannah.